let's say I have done testing with 1000 piles, and the running time is really not much different. The output is just like instant. And number of piles. If we have 10 piles with random stones on each pile, running time will be 10 to the power of 2, and therefore 100, and therefore 100 commands for the machines to run. And if we have 9 piles, and it will be 81 commands. We have 11 piles, that will be 121. From 9 to 10 piles, it is only increased 9 commands, but from 10 to 11 piles, it increases 21 commands. And as we can see, it is quite a larger difference between 9 and 11, and therefore larger number of piles are more impactful comparing to smaller number of piles. So the limitations and constraints about this game itself, it have a fixed winner. Although all the variables can be random, we can still see who the winner is at the start of the game if we assume that both player plays best. There will be unfair situations, although it is rare, but it is possible. For example, from before, if we had 3 piles of 1 stone each, then player 1 would win no matter what, and there's no winning or gaming experience for player 2. And third one is it's not player friendly. If we're thinking about a larger number of piles or a larger number of stones, it is quite hard for the player to count or to remember which pile and which stone to remove, and etc. Now let's go to the second solution method, minimax and alpha beta pruning. So with this part, it have 2 parts. The first one is minimax. It's the calculation of the optimal move available, and the second one is to reduce the search nodes, so therefore improve the computing speed of the algorithm. First, minimax. This is a theory aims to find the optimal move for a player at each different stage. It minimizes the greatest risk to provide a winning strategy. So how this works is if you're thinking about the algorithm itself, it takes a set of arrays that indicates the number of moves available at each stage, and it searches through each one, and it searches through each array and decide which move is the best at the current stage. And if we look at the example below, that will be an array of only 1 pile consists of 7 pieces, and it shows every single move possible until it moves to 0. And we can see that is quite a lot for just 1 pile. And here we have a similar search tree, but with multiple piles uncompiled together. When multiple, what I mean is 2 really. It's just 2 piles compiled together, and we can see the calculation or the searching steps it takes increases dramatically. Yep, so if we look at pile increases, for example, even just 5 piles, the number will increase by the power of piles increases. And the running time complexity for this algorithm particularly is big O n to the power of n. And therefore, if the power increases to number, for example, 87, which I'll show the result later in the PowerPoint, it just will not run because the running complexity is out of the handling of my laptop's hardware. So therefore we introduce alpha beta pruning. What this does is it removes all the useless or similar or not as good not passes, and only search through the best one. And here we have the example. In the image on the right, it stops searching through the second node because the number there it already result in 5, and that is greater than the previous node, which is 3. If we're assuming that if we are setting that larger numbers are worst comparing to small numbers. And the implementation. So if we were to implement um, minimax and alpha beta pruning, this will have three major functions. The first one, it will be the dataset generator. The dataset generator will generate all the tree nodes, and that will be used as inputs for the other two functions. And minimax, this function will take the array list of arrays as input and display number of stones to remove and which piles to remove from as return. And alpha beta pruning will be a function written separately and will be used within minimax to reduce the number of nodes to search for, and they'll most likely be a comparative factor as explained in the previous page. So the impact of number of piles on this particular algorithm. The example here we have on the left, it will be 2 piles of 7 stones, and we can see the number of piles is just doubled from there. But with alpha beta pruning, the running complexity will be reduced because it will switch through only the first step and it will recognize it is the same as the previous node, so it will stop searching from there, and mathematically it will just be n to the power of n divided by 2. Limitations and constraints. This algorithm only assumes when the both players are making the best moves available. However, it does not consider the fact, for example, if someone misread the information or have not considered some factors and makes a not so well thought move, then the algorithm will have to search through that current stage again. And the second problem is that the running complexity is too high comparing to dim sum, because most of the times a will have to consider all the factors available and not just thinking about the quickest one. And as I tested before, it is impossible to generate dataset that is pile number anything above 81 in my case. And the hardware requirement will also increase as the number of piles increases, but because we're limiting number of piles between 2 and 5, so that is not really a problem at all. And thank you for listening. So the Python implementation of minimax and alpha beta pruning is provided on this following link. I have not implemented Python code of this particular algorithm myself, but I did with minimax. So, but I did implement my own code with dim sum. And I'll be reporting more about my research and references in my report. Here is the running game for and here I'll just make random moves and just to display how this one works. Let's just say 1 and I'll just say take all. So other than other than lectures I have learned from Unisite, this is some of the resources I have learned from online. Here is what it looks like when you run the program.